Okay, we're at the Shimatsu and we're ready to come in and pull a tensile test on our sample, but the first thing you probably want to do is clean it up. Go take your hardness test, take your measurements of your cross-sectional area here. What you do is come in here and lay out our gauge lines. Now what I'm going to do is make sure the scale itself is going to be parallel to this surface on the part. And I also want to check and make sure that the radius, I'm at the tangent point, that I can get the 2-inch gauge length between the two tangent points of that sample, which is really close. So I'm basically there, and then what I'm going to do is with this screwdriver, it's really sharp, we sharpened it up, I'm going to come in and scribe that line right there on the sample. I don't know if we can see that, but if I get the light on there, I can see a line representing the start of my 2-inch. Then what I'm going to do is I'm going to turn it around so that I can show you on the screen here, and I am going to come in. And I guess the best way to do this for you guys is to come in, and I can see my line start right here. So I'm going to get it lined up with this 4, and I know up here is the other 2, and I am running pretty parallel, and I'm going to lay out another line, and that's going to be my 2-inch gauge length. So at this point, if I get this right, I have 2 lines which represent my 2-inch gauge length. I'm going to be using those after I pull the sample to calculate my percent elongation. Let's learn how to use the computer a little bit.
I want to talk a little bit about the screen that we have up here. We have some folders. Now these are going to relate to different courses, and every semester it's going to change in terms of how many and what courses are on there. But if I want to go in there, and let's say we're in 3311, that's the material science lab, I could create subfolders, and each group can create their own folder. So if you're in group 10 or 20 or 30 or 40, create a folder that's going to be where you can store your files. So I am doing mine under demo, and I created a subfolder for Tensile, because you may come to these machines and do a variety of experiments from tensile, compression, creep, all those kind of things on the machine. This is a great idea to keep the data on the machine so that if you lose your flash drive, the data becomes corrupt. You can always come back here. Another powerful tool on this computer is sometimes you may just want to do a screen capture, especially if you're in a course like 2141. So we can come in here and use the snipping tool. Now in the snipping tool, they have 2 features I like. I like the rectangular snip and the full screen snip. Now the rectangular snip is going to be powerful because if I just come in here and say new, it will let me just do a portion of the screen right there, and I can say file, save as, and I can save that anywhere I want. Now if I go in the snipping tool and I say I want to use full screen mode, it will capture the whole screen, and I can say save as, and I have that whole screen. So if I had a graph on there, for example, and I just wanted to capture that because it will display the maximum load and the yield point and possibly put it in the reports on different testing methods, then that's going to be a great tool for you just to have that JPEG for your report. Now inside of this desktop, we have a folder called Trapezium. Trapezium is the software that is going to run the Shimatsu machine. To log into this, we have to type in user, and user is the password. Now, you're just users, and you're not going to be able to create methods as a user. If you're needing to create methods, you're going to have to get with Professor Lewis, and we're going to have to, which is me, and we're going to have to sit down and look at what test method and what it's going to be used for. Now, what is a test method? I'm going to click on this, select test method. These are basically, how is that machine going to conduct that experiment? Is it going to apply the load by just a certain load rate or a certain stress rate? Is it going to go positive in a tensile or negative in a compression? How's it going to interpolate the data and present that to you? So we have all that kind of stuff already preset in all these kind of testing methods. What we're going to do in this demo is we're going to leverage this testing method for the inch, and I'm just going to say finish. I've picked it, and it's going to go directly in here where we can do a tensile test. Now this tensile test is just going to give us the ability to pull a test, and we're going to be able to download the raw data, and you're going to be taking that to Excel and creating your stress strain diagrams. Yes, this software will create that stuff for you, but we want you as part of the class and the program to create your own stress strain diagrams. Now let's talk about our screen, what we have going on here. The first thing we're going to have to do is talk about force right here. Force is dealing with the load cell on the machine. If it's the very first time we turn the machine on, or it's at the start of the lab, we may want to come up here and just hit calibration. Now when we hit calibration, you want to make sure you don't have a sample loaded, there's no force, and that's going to be applied to the top templin grip up there. So you don't want to be messing with the machine, jogging it, moving it. And you notice it's saying it's performing ecal. That's going to take a little bit, and it will tell you when it's done here, and it will beep at you. And then we know that load cell is calibrated. Once we calibrate the load cell, it's pretty much going to be calibrated for all the samples you're going to be pulling. So you don't have to calibrate every time, just this one time. And if you didn't calibrate when we first turned it on, it will error out and tell you you need to calibrate the machine. Now it just beeped at me and it is now calibrated. What we're going to have is basically a graph. It is set on auto scaling, so as the load increases and we start elongating that part, it's going to go off the screen here. It's going to automatically rescale and keep it sized up on the screen where we can see it really, really well. So you can watch the nice red trajectory of the actual plot that's going on there. Now, what we're going to do is we're going to be able to hit start test once we have the machine ready. Now, some of the things we're going to need to have for the machine to be ready is load our sample. So we'll have to go over there and load our sample here in a minute, and then we're going to come in here and zero out all three of the force, the stroke, and the extensiometer. And to do that is just anytime we want to do that, you just right click and it zeroes that column out. So let's go over to the machine and load our sample.
So we just turned on the computer and we zeroed out our load cell, which is up here on the top of this platen here, which is connected to this top templin grip. And we're ready to actually load our sample at this point. So when we do that, we're going to have to learn how to raise and lower this top platen. And to do that, we're going to use this controller over here. So we can come in here and hit hand jog, and this is going to be in the slow mode. If I raise up, you can see it's moving, and that's going in the positive. So you want to make sure you're going in the right direction so you don't crash the machine over there. I can move high speed, and it's going to come up at a much faster rate there, a lot more displacement. So you've got to really be careful with that. It's beeping because it lets us know we're in high speed mode. When we're done adjusting the machine, we need to come in here and hit stop, so then we can conduct a test. If we're in jog mode, it'll say on the controller over there, when we try and run the test, that there's an error that you're in manual mode, and that means that we have the jog button pressed. So once we have that done, I'm going to take that off, and let's go load our sample. So this is the extensiometer that's going to measure our elongation. We have our 2-inch gauge length on this one. And if you notice, there's a little pin in here right now, and we want to be careful not to tear the cord up. This little pin is maintaining that 2-inch gauge length. When we store it, we want to have the pin in there. We want to lay it down there carefully on the bottom platen so it doesn't fall and get damaged or broken. Now this is basically has springs in it that if I push these springs, it will open up, and that's where we're going to grab the part down there. Now when I put this on here, I'm going to put it on the part, and I want to make sure I'm pretty well centered up on the part equally on each side. The other thing I'm going to do is I'm going to reach in there when I have it in the machine. I'm going to hold the extensiometer, and I'm going to carefully slide this pin out and make sure that nothing moves. That's going to maintain my 2-inch gauge length. Right now it's ready to pull a test. So I'm going to go ahead and put this back together, take my sample out, and let's go load it in the machine. To load the sample, we want to pay attention. There's a series of measurements lines here and also up here. We're going to make sure that we have that sample not pushed off to one side or the other. You want to make sure that you're holding on to the tangs of the sample on the dog bones correctly. Now what I'm going to do is load this one in here, and I'm looking at the lines, making sure I have it pretty evenly spaced, and that's turning that templin grip the wrong way. If I turn this one counterclockwise, so counterclockwise on the bottom one is going to allow you to tighten. And again, I'm going to come in here and snug that up. And so this is going to be tight, and it's going straight up. And if I look, this one's going to be aligned at the top, so I know I'm perfectly unilaterally loading this thing, and I don't have it in a bending moment. So now I'm going to come in here and turn this one clockwise on the sample, and now I've tightened the top grip and the bottom grip. As this machine pulls, they'll tend to tighten up the rest of the way, so you don't have to really get on those and bear down and tighten them up. Just past snug is probably going to be doing a good enough job. The next thing we want to do is come in and put our extensiometer on there. We talked about how to put that on there. I'm going to push those springs. I'm going to find where I need to put it right there. I'm going to come in here and carefully hold it, other end of the extensiometer, pulling that pin out, and nothing's moved. So this is armed and ready for taking our test. The next thing we got to do is lower our safety shield, and up on the controller make sure we hit stop so that it takes it off the jog mode / the manual mode.
We've loaded our sample into the machine. We're ready to come up here and zero out, and you just right click on the force area here, this blue area, and then right click on the stroke and right click on the extensiometer. These are all now zeroed out. It's okay if you get a little fluctuation on there. That could be vibration in the machine. We're going to be able to start the test, and we're going to watch the plot, and it will automatically scale, showing us that data. So let's come in here and start this. We're going to hit start. Now you should at this point have the safety door all the way down. You need to double check and make sure that the controller is off on the jog mode, that it's not doesn't have a light on, or they will come up here with error messages, and you're going to have to go do those and then just reset the error messages. So I'm going to hit start test, and you can tell we're going up in a nice linear fashion here. We're off to the races, and it's auto scaling as it comes up here and hits this, and we can see the loads that we're hitting on that sample, and you can tell it looks a little sloped here. And we've passed the yield somewhere here. This is a really soft steel. This is A36 steel. And what we're seeing is that yield point's not as defined as maybe a stronger steel. And so we're headed off here towards our UTS, and we'll be looking for the load to see where that load doesn't change anymore and it starts going down. We're still climbing towards the UTS at this point. Again, you can see we've got a lot of data out here. So when you guys do your stress strain diagrams, we're probably not really interested in this kind of data, more so the data of the UTS and right here. So we're still climbing and climbing. Look at our extensiometer here. We're already at 100 thousandths of an inch. We're getting close to about an eighth of an inch for some of you think that. And look inside, and you can see the displacement on the extensiometer where the holes and the extensiometers are separating. I see the necking starting there in the middle, and there it broke. You didn't hear it. You just heard a little thud. You guys are going to have to export your data. So how do we export our data? The thing you don't want to do is to hit save. If you hit save, that's going to save that in a trapezium format that the software only can read, and Excel can't read that. What we're going to have to do is export the raw data out, and to do that we're going to come up here and say File, Export, and we're going to go to Raw Data. Now what this is going to do is take us to a comma separated file format, and we can bring that into Excel. So I'm going to call this, and I'm just going to call this right here A36 steel, and I'm sending it to my folder on the desktop that we talked about a while ago. So I now have that into the system. Here's my A36 file. This is a common separated file. There's a comma between each roll, each column I should say, for that roll, and it has a header: time, force, stroke, and extension. So time is the time that we took it, the force, the stroke, that's the stroke of the machine itself, and then the extensiometer is the data from the extensiometer.
So the last thing we need to really do here is document some dimensions and record the fractured surface of our part. And so to get the dimensions that we're going to need to put our part back together, and from our gauge lines we're going to come in here and you're going to measure those with the dial caliper from one line to the next and record that measurement. Also what you need to do is come in here and measure the thickness and the width of your sample and record that in your lab sheet as well. And then the last thing, we're going to go to the zoom microscope, and we're going to come in here and we're going to take a nice picture of our fractured surface and put that in our report. So we're now at the computer that we can actually look at the broken fractured surfaces on our microscope here. We can move this microscope up and down. We want to leave it somewhat the same. I have it set where we can do the coarse and the fine adjustment back here in terms of focus. So what we want to do is from the table up to the certain table height, the TA is going to tell you how high that is. And currently I'm doing it at about 3.1 inches. So if I was going to measure a part, I could use these nice little paper clips. They come in great for holding my part. And I can take my steel ruler here, and 3.1 inches, I can come up here and line up my top of my part with that, and that's going to be in the focal length. So if I put it in there, now I can do the fine tuning on my focus and get my sample in focus. So let's go up here and hit the green arrow for the play arrow, and it's going to show me what's in the microscope. Now I'm making it look easy. You guys are going to have fun trying to get this in the field of view and focus, and you're going to learn that just touching the machine is going to take it out of focus. The other thing we have over here is a light control, and you want to adjust the light to where you get a really good image, what you think is going to show the most in that image. Now once you get that image up and where you want to see it, okay, you're going to come in here and you're going to go to File, Save As, and you can now save that as a JPEG in the folder on the desktop, and then in your group folder, just like we've talked about before, and now you have that image for that broken sample. You can do this with each broken sample, and this way you can get a real good feel of what that fractured surface looks like. The one thing we have left to do now is just go out there, do our Excel spreadsheet, create our stress strain diagrams. So let's go watch that video.